Welcome to the new lesson HDFS Concepts. In this section, we'll look in depth about HDFS. Let us start with the terminologies used in HDFS. HDFS is a distributed file system. That means the files are stored across a cluster of computers and not just one. A cluster is nothing but multiple racks put together, and a single rack is nothing but a lot of computers put together, which are individually termed as nodes. In HDFS, these nodes which store data are known as data nodes. They act as worker or slave nodes. Name node, which is the master node, is responsible for the management of the files that are distributed across the cluster. Let us see a simulation on how a file is stored in HDFS. Files are broken up into smaller chunks, also known as blocks. These blocks are then replicated. In this case, they are replicated by a factor of 3, which is the default multiplication factor of HDFS. These blocks are then distributed over the cluster, and this process of replication and distribution is managed by NameNode. NameNode keeps a track of complete file system and block locations. If you notice, the distribution done by NameNode is smartly done, so as to provide resilience if a failure happens. In this case, suppose if one data node fails, NameNode would still be able to put together the complete file with the help of replicas. If suppose a complete rack fails, even then NameNode would be able to put the file together. We'll learn later what considerations the NameNode takes to distribute the file blocks. Let us understand the ideas behind HDFS. HDFS is designed to handle large files of hundreds of GBs and TBs and more. Data access is not quick with random reads and writes. It is found out that the data access patterns of write once and read many times is the best served for the data analytics. HDFS is designed to use commodity hardware, but it is definitely not cheap hardware. A typical unit would cost around 1K to 5K, which would be available with many vendors. Typical installations of RDMS server can take up to 50K expense on hardware itself, which has an upper limit of processing. But this as well means that the hardware failures would not be a specialty case but a norm in HDFS. As the cluster size increases to thousands of nodes, hardware failures may happen every other day or might happen every other hour. As we study the HDFS concepts, we would see that it is equally important to learn about the failure scenarios as it is to study stable processing states. Next, we look at what HDFS is not designed to do. It is not designed for quick read of data. It cannot function as OLTP database. For that, we definitely need RDBMS, at least in the present scenario. HDFS also doesn't work well with a lot of small files. HDFS doesn't support arbitrary file modifications as well. Only append is supported. Let us understand the most important fundamental to any file structure, that is, its blocks. Block size is the minimum amount of data that can be read or written in a file system. But block size in Hadoop is a little different. First, it is big. While it is common to have a block size of 512 on a storage media, its default size is 64 MB in HDFS. That is 128 times more. Second, if a file is stored in HDFS is smaller than the HDFS block size, then only the amount of size that is needed is utilized and not the complete block. There is a reason for a large block size. We had discussed earlier how seek time becomes a bottleneck while processing large files. So the idea is to keep the seek time around 1% of transfer rate. So considering 100 Mbps transfer rate and 10 milliseconds as additional seek time overhead, the block size would have to be 64 MB or upwards to keep the seek time around 1% of the transfer time. In the next section, we would learn in depth about HDFS architecture.